Hello, AP Chemistry students. We're now on the second and final part of Unit 6 on reaction enthalpy. And this is going to be focusing on sections 6.7 through 6.9. Our learning objectives here are to calculate the enthalpy change of a reaction based on the average bond energies of bonds broken and formed in a reaction, to calculate the enthalpy change for a chemical or physical process based on the standard enthalpies of formation, to represent a chemical or physical process as a sequence of steps, and to explain the relationship between the enthalpy of a chemical or physical process and the sum of the enthalpies of the individual steps. Now, you might not have noticed this, but you might be wondering what happened to section 6.6, and I realized it after the fact that I actually covered it in part 1 without realizing it, so don't worry about it. So, in a chemical reaction, energy is absorbed to break bonds and released when new bonds are formed. A good way to think about this is to think about the electric potential in magnets. When you hold two magnets apart from each other, they have a attraction to each other and they're going to snap together. And that releases that potential energy. So that's like new bonds being formed. And then when you try to pull those magnets apart, you're going to have to put in energy to overcome that force. So by the same logic, energy is absorbed to break bonds because we need to put in energy to pull atoms apart. And energy is released when new bonds are formed because they are attracted to each other and they release some potential energy as that bond is formed. And this means that overall, the process of breaking bonds is endothermic and the process of forming bonds is exothermic. And when we relate that to an energy diagram, when we're kind of getting to our activation energy at the top here where the activated complex is, that's kind of when bonds are being broken. And then once that energy is released and we relax back down to the products, that's when the new bonds are being formed. And depending on whether we're an exothermic reaction or an endothermic reaction, which one of those two sections, either the bond breaking or the bond forming, is going to be more energy. If the energy absorbed to break the bonds is less than the energy released when bonds are formed, that's going to be exothermic overall because the net difference is going to be a loss in energy. That also means that the products are more stable. They're more comfy. They're at a lower energy. And for a endothermic reaction, if the energy absorbed to break the bonds here is more than the energy released when bonds are formed, it's endothermic overall because the reactants are more stable and the net change in energy is positive. All right, and the overall energy of the reaction is always going to be dependent on the difference between the energy in the bonds of the reactants and the energy in the bonds of the products. And we talked about this last time. This overall energy change is called enthalpy and is represented by delta H. And if we're going to calculate that delta H, it's going to be equal to the sum of the energy of the bonds broken minus the sum of the energy of the bonds formed. This is a capital sigma in math that usually refers to a sum. Now, you're going to usually get a table like this or just a list of values that tell you the energies of different bonds if you're going to be asked to solve problems like this. And you'll notice that the delta H has a little degree symbol next to it. That means standard state conditions. This is kind of like STP, but it's a different set of values. It's notated as delta H with a little degree symbol, and it assumes that all gases under these conditions are at 1 atmosphere, all liquids and solids are pure, all solutions are 1 molar, the energy of formation of a pure substance is 0 kilojoules per mole. You'll understand what this means later, and that the temperature is 25 degrees Celsius or 298 Kelvin. And this is one of the most important factors because this is also where it differs from STP. If you recall, standard temperature and pressure was 1 atmosphere and 0 Kelvin, or sorry, 0 Celsius. This one is 1 atmosphere and 25 degrees Celsius. So standard state conditions is more focused on a room temperature type state. So let's try an example of calculating the reaction enthalpy. So let's look at it for the formation of water from oxygen and hydrogen. So we have 2H2 plus O2 making 2H2O. And when we're calculating the reaction enthalpy using the bond enthalpies, it is really helpful to know what kinds of bonds that we have. So it's helpful to draw out the Lewis structures of the molecules involved. So we have our two H2s, both with a single hydrogen-hydrogen bond. We have our O2 with a double OO bond. And then we have H2O, which has 4 OH bonds. So these are going to be the bonds broken, and these are going to be the new bonds formed. So we can refer to our table, and since we're doing the sum of the energy of the bonds broken minus the sum of the energy of the bonds formed, I can set up an equation where first we have, where's hydrogen? Hydrogen, there it is, 436 kilojoules per mole, and there was 2 of them being broken, and then that's going to be summed up with the other bonds broken, which was the OO bond, the OO double bond, and this table is a little bit odd, but the OO here is O2. It's assumed to be an OO double bond if you know what the Lewis structure of O2 is. So that's 495 kilojoules per mole. So we're going to sum that up, and then we're going to subtract the bonds being formed. And the bonds being formed were just OH bonds, but there was 4 of them. And that's 463 kilojoules per mole. We multiply that by 4, and then we calculate all of this. We end up getting negative 485 kilojoules per reaction as written. And what I mean by that is if when I have 2 moles of hydrogen plus 1 mole of oxygen combining to make 2 moles of H2O, this is the exact amount of energy for that process. So let's try another one. What is the enthalpy of reaction to form ammonia? So this time we're looking at N2 reacting with 3 H2s to make 2 NH3s. Once again, I'm going to draw out the Lewis structures so I can see what kind of bonds we have. We have a triple N bond for the bonds broken, as well as 3 HH bonds. And then we're going to form 1, 2, 3, 4, 5, 6 NH bonds. So I can set that up. I can look up the values. The value for an NN triple bond is 941 kilojoules per mole. And then we have 3 times the value for the HH single bond. And then we're going to subtract the bonds formed, which was 6 NH bonds, which all have an energy of 391 kilojoules per mole. And when I compute it, I get negative 97 kilojoules per reaction written. So for every 1 mole of N2 reacting with 3 moles of H2 to form 2 moles of NH3, there's a release of 97 kilojoules of energy. All right, so another type of value that we can use to calculate reaction enthalpies is the heat of formation, notated as delta H with the degree symbol and a little f as a subscript. And this is defined as the change in energy that takes place when 1 mole of a compound is formed from its component pure elements at standard state conditions. So what this might look like for CO2 is CO2 being formed from pure oxygen and pure carbon. And it has a value associated with it. So for CO2, the heat of formation is negative 393.5 kilojoules per mole. And I said something earlier about the heats of formation in regards to standard state conditions. The heat of formation of pure elements is assumed to be 0 kilojoules per mole. And this is gonna make sense later when we start summing up things to make heats of reactions overall. And yeah, just remember this as one of the assumptions of being at standard state conditions, and it'll make sense later. All right, so heats of formations are also usually given on a table or a list. The different things will have different values associated with them. Also, please make note that like liquid water versus gaseous water, depending on the state of matter they're in, they're going to have different heats of formation. So in early examples, we used bond enthalpies to calculate the heats of reactions. And we technically simulated heats of formations in those because we had water being formed from its component elements. We had ammonia being formed from its component elements. And in those, I said there was this much energy per reaction as written based off of the mole ratio in that equation. However, if I wanted to convert these values that we calculated into heats of formations, I'd want to consider making just 1 mole of the product, 1 mole of the substance of the compound based off its pure elements. So in that case, since there's 2 moles of H2 being formed here and 2 moles of ammonia being formed here, I can just take these 2 values and divide them both by 2, and that will give me the heats of formation of water and ammonia, respectively. Now, if you look at these 2 values and compare them to the ones on the table, they're slightly different. And I wouldn't worry too much about that because I've seen a bunch of these different tables and the exact values that are given are sort of dependent on the sources for those values and the data and how it was collected. So as long as you're using the equation correctly and processing the numbers correctly, I don't think it's going to matter the exact values that you use, or sorry, I don't think it's going to matter if the values you get from calculating the reaction enthalpy using the bond enthalpies matches the values from the heats of formation. So wouldn't worry too much about that. So since the delta H, the enthalpy of a reaction, is still based off of the difference between the energy contained within the products and the reactants, we can use a similar equation to calculate the heat of reaction using heats of formation that we did using the bond enthalpies. Now, for this equation, it's going to be the enthalpy of the reaction overall under standard state conditions is going to be equal to the sum of the heats of formation under standard state conditions of the products minus the sum of the heats of formations under standard state conditions of the reactants. Now, you might notice that this equation is a little bit different than the one we did before, where it was the sum of the energy of the bonds broken minus the sum of the energy of the bonds formed. And the point I'm making here is that this is products minus reactants, and this is kind of technically reactants minus products. And that just has to do with how the math is calculated. So please take note of that. All right, so since the equation is the sum of the heats of formation of products minus the sum of the heats of formation of reactants, we can use that in conjunction with a balanced chemical equation and a list of the heats of formations of the products involved in order to calculate the reaction enthalpy. So in this one, we have 2 moles of NO plus O2, making 2 moles of NO2. And I have all of the values given here. And note that the O2 is 0 kilojoules per mole. So like I mentioned earlier, all pure substances, all substances that aren't compounds under standard state conditions are assumed to have a heat of formation of 0. So let's calculate this the same way that we were doing it before. So the heats of formation of the products minus the heats of formation of the reactants. We're going to start with the NO2, which is a value of 33.18 kilojoules per mole. I'm going to multiply it by 2, and that's the only product, so I'm going to bracket that off, and then I'm subtract the heats of formation of the reactants. We have NO, which is 90.25 kilojoules per mole, and we have 2 of them, so we multiply that by 2, and then plus 0 kilojoules for the oxygen, being a pure substance with a heat of formation of 0. And then I compute it, and I get negative 114.14 kilojoules per mole. I'm not too worried about sig figs in these cases because these are all just relationships, values measured from a table, no actual like laboratory measured values. So don't worry too much about sig figs on these ones. Now, a place where sig figs are going to matter is if we are using this value in conjunction with a measured value. For example, say I wanted to calculate how much energy is released when 20 grams of NO reacts with excess O2. So I could start with my 20 grams. I can convert it to moles, and then I have my moles of NO. And now I need to consider that the value that we calculated here, this is how many kilojoules per mole of the reaction as written. So that's implying that 2 moles of NO are reacting with O2 to make 2 moles of NO2. So I'm going to want to relate NO to the overall equation. I'm going to want to know what the ratio of NO to the entire process is. And that means that there's 2 moles of NO per 1 of the whole reaction. So I use that as a step here. I convert moles of NO to moles of the reaction overall so that I can use that value that we calculated earlier. So I have 20 divided by 30.01. That gives me moles of NO. I turn moles of NO into moles of reaction, and then I can multiply that by the heat, the enthalpy of the reaction overall. That gets me here negative 38.03 kilojoules. Let's try another one. Let's calculate the enthalpy of the combustion of glucose. So we have C6H12O6 plus 6O2, making 6 CO2 gas and 6 water vapor. So I mentioned this earlier, but we want to make sure that we're using the right states of matter of things. So we're going to be want to be using the water vapor value here instead of the liquid water value. So let's get everything plugged in. So it's products minus reactants. So I'm going to have the 6 times the CO2 value plus 6 times the water value. Bracket that off. And then for the reactants, I have the value for glucose. And then for the oxygen, it's just going to be 0 kilojoules per mole since it's a pure substance. Oops, these are supposed to be per mole. All right. And that gives me an overall value of negative 2,551.8 kilojoules per mole. Now, say we wanted to calculate how much energy would our body gain if we consumed 100 grams of glucose, this being a sugar that our body breaks down. Well, I could do the same thing I did earlier. I can convert it into a dimensional analysis problem. I start with the 100 grams. I divide it by the moles of glucose. And then I recognize that in the balanced chemical equation, there's 1 mole of glucose per mole of reaction, as you can see here. Oops. And then I multiply that by the value of energy per mole of reaction that we calculated in our enthalpy equation. And that tells me that there's negative 1,420 kilojoules released by the reaction. And that should be dot there to make it proper sig figs. And this is the energy being released by the reaction since it's a negative. So if the question was asking us how much would our body gain, how much would our body absorb, we're treating our body as the surroundings and the reaction as the system. So that means that there'd be a positive 1420 kilojoules absorbed by our body. So let's think about what a positive or negative enthalpy value looks like in terms of physical observations of chemistry. So this is a demonstration I usually like to do in the classroom, even though it's a little bit dangerous because it forms ammonia gas. But in this, we have barium hydroxide hydrate reacting with ammonium chloride. We have two solids that are going to make a gas, some liquid water, and some barium chloride. And it has an overall enthalpy of reaction of 164 kilojoules per mole. So a positive enthalpy, therefore an endothermic reaction. And if this reaction was done in a flask, what would we expect to happen to the flask? Well, if we treat the flask as the surroundings and the reaction as the system is going to be absorbing energy, so it's going to be taking it from its surroundings. So that means that the energy of the flask is going to go down, so we'd expect it to get cooler. So let's see this in action. So this is a video that I stole from Berkeley Chem Demos on YouTube. And in this case, we have two beakers full of our solids, our barium hydroxide hydrate and our ammonium chloride. And then on this wooden block, they're putting a little blob of water. And this is going to help us track sort of the endothermic reaction. You'll see why in a sec. So they mix these two solids, and then they have to stir them vigorously because it's really hard for two solids to react because they aren't in an aqueous medium, and it's not easily able for those particles to run into each other. And as they put it on top of the moistened block, the reaction is starting to occur. And then you can see that that block has now frozen to the bottom of the beaker due to the little droplet of water there turning to ice. Anyways, I think that's pretty cool. Let's change gears now. So if a reaction can be described as a series of steps, then the enthalpy for the overall reaction is going to be the sum of the enthalpy of all of the individual steps. And this is an idea called Hess's law. So for example, say you have A becoming B, and that has an enthalpy associated with it, and then B becoming C has one, C becoming D has one, and D becoming E has one. But say I only want to know the enthalpy of A becoming E overall, so the reactant going to the final product, ignoring all of the intermediates. Well, since all of these steps have an enthalpy associated with them, the enthalpy of the full reaction of A becoming E is just going to be the sum of all of those individual enthalpies. So sometimes the enthalpy of a reaction can't be measured directly, so we use Hess's law to estimate it by turning it into a several-step reaction and summing them to get the total. And let's look at an example of that. So say we're studying the reaction of 4 ammonia plus 5 O2 becoming 4 nitrogen monoxide and 6 water, and we're told that it can be split up into the following steps. You're never going to have to determine those steps on your own. You'll always be given some context for them. So we have N2 plus O2 making 2NO. We have an enthalpy associated with that. We have N2 plus 3H2 making 2 ammonia. You can see these all kind of look like heat of formation reactions. We have 2H2 plus O2 making 2H2O. And we have enthalpies associated with all of these steps. Now, the trick here is that you'll see that there are things in these equations that aren't in the total. So what we're going to have to do is we're going to have to take these 3 steps and manipulate them and in order to sum them all up in a way that equals the total equation. And the rules for this, based off of Hess's law, is that if we manipulate an equation by, say, like flipping it backwards, turning the reactants into products or the products into reactants, we're going to flip the sign, since the enthalpy of the backwards reaction would be the opposite. Like a reaction that's going to absorb a bunch of energy, if we were to look at that reaction backwards, it's going to release a bunch of energy. And also, if we multiply or divide everything in the equation by an integer to get the right number of moles of something, the right coefficient, we're going to have to do that same mathematical manipulation to the enthalpy as well. So let's start working on this. It's kind of like solving a little bit of a puzzle. So I want to get this overall reaction with 4, 5, 4, and 6 moles respectively. And with everything on the right side, ammonia and oxygen are reactants, and nitrogen monoxide and water are products. So let's look at our reactions. We need to figure out which ones are going to be flipped and which substances we're going to need to cancel out. So we want to get ammonia and oxygen on the on the reactant side. It looks like these two already have oxygen on the reactant side. Here's ammonia, it's on the product side. So we're going to want to flip this middle one. And also, if we're considering which substances need to get canceled out, N2 and H2 are not in the original equation. So we're going to want to get N2 on opposite sides of the equation so that they cancel each other out. All right, so like I mentioned, we're going to flip the second equation to get ammonia on the reactant side. And I turned the negative 91.8 kilojoules per mole into positive 91.8 kilojoules per mole. And I think that gets everything on the right side. Let's see. NO is on the product side, water is on the product side, ammonia on the reactant side, oxygen on the reactant side. Okay, so I don't have to flip anything else. But you can see here that the values of these equations, when we sum them up, are not going to equal those in the original equation. So we're going to have to multiply each of these equations by an integer in order to get it to sum up correctly. And remember that we're going to also have to multiply our enthalpy values as a result. So I multiply the first one by 2, since it was 2NO and I want 4NO. So I'm going to multiply by my enthalpy by 2. For the second one, it's also going to be multiplied by 2 since I want 4NH3 and I had 2 in the original equation. And then the last one, since there's 2 waters and I need 6, I'm going to multiply that by 3. So then I end up with these now manipulated chemical equations. And hopefully, if we've done this correctly, they're all going to add up to make our final equation. So you can see here that 2N2 and 2N2 here are now on opposite sides, so they cancel out. 6H2 and 6H2 here are now on opposite sides, so they cancel out. And overall, I have 4NH3 plus 2O2 plus 3O2, so that's 5O2 overall, plus 4NO plus 6H2O on the product side. And it looks like we have done it. So now in order to get the enthalpy of the overall equation, I'm going to sum up all of the enthalpies of the individual steps. And you can see that here, once we do that, we get negative 906 kilojoules per mole overall. All right, so let's do another practice. This is a slightly easier one. Determine the enthalpy of the following reaction of CuCl2 solid plus copper solid, making 2CuCl solid. And we're given the following steps. We have copper plus chlorine, making this copper 2 chloride. And then I have 2 copper plus 1 chlorine, making 2 copper 1 chloride. Each of these have a enthalpy value associated with them. So let's see. I need to get the copper 1 chloride on the product side and the copper 2 chloride on the reactant side. I can see here copper 2 chloride is on the product side, so I'm going to want to flip this first reaction. So I can cancel that out. I flip it. I change the sign. And let's see, is this going to be good enough to get us to the overall reaction? We want to cancel out the chlorine. We can see that's going to happen here since it's on opposite sides. And I have 1 copper on the product side here and 2 coppers on the product side here, which is going to be convenient because I have 2 coppers here, but I only want 1 in the equation. So the chlorines are going to get canceled out, and the copper on the product side is going to cancel out 1 of the coppers on the reactant side, leaving 1 behind. And then I have copper chloride plus 1 copper, copper 2 chloride plus 1 copper, making copper 1 chloride. And then since I flipped the first reaction, I just changed its sign, and then I'm able to sum these together, and I get 70 kilojoules per mole for my final answer. All right, let's look at another one. Determine the enthalpy of the following reaction. We have PCl3 plus chlorine gas, making PCl5, and we're given the following steps. We have 2 pure phosphorus plus 3 chlorine, making 2 PCl3, and then 2 pure phosphorus plus 5 chlorine, making 2 PCl5. All right, so we want the PCl3 to be on the reactant side and the PCl5 to be on the product side. So we can flip this first reaction. and I'll flip the sign. So now we have 2 PCl3 on the reactant side, 2 PCl5 on the product side. We're going to want to cancel out the pure phosphorus, which is already in the same amounts in both. But you'll also notice here that in the original equation, it's 1 PCl3 and 1 PCl5, whereas I have 2 in both of these. So not only can you multiply these things to manipulate them, you can also divide by something to manipulate them. So I'm going to want to divide both of these equations by 2. And I'm going to end up with PCl3 making 1 phosphorus plus 3 halves chlorine. And I can then divide the enthalpy value by 2. And then for the second equation, I'm going to have pure phosphorus plus 5 halves chlorine, making PCl5. So now these are in the right amounts. This was also divided by 2. And the fractions might be a little bit confusing here. But if you think about 5 halves chlorine on one side, that's equal to 2.5 moles. And then 3 halves chlorine on the product side, that's equal to 1.5 moles. The 1.5 is going to cancel out 1.5 on this side, and then 2.5 minus 1.5 is going to be 1 chlorine left over. So the sum ends up working to give us 1 chlorine on the reactant side, 1 PCl3 on the reactant side, and then 1 PCl5 on the product side. And then I'm going to sum up both of these values. The first one was flipped, and then they were both divided by 2, and then I get a total of negative 123 kilojoules per mole at the end. All right, lastly, let's look at a slightly more complicated one. So we have 2 aluminum solid plus 3 chlorine gas, making 2 aluminum chloride solid. And this is given, this one's broken up into 4 separate steps. So let's see, we need to identify what needs to be on the correct sides and then figure out what we also need to cancel out. There's going to be a lot that we need to cancel out in this case. So 2 aluminum solid, that's already on the right side. So we might want to leave this first one alone. We have this hydrochloric acid, this HCl aqueous that we don't need, and there's 6 of them. So we're going to need to have 6 of those somewhere else to cancel them out. So we can see in this second equation, we have HCl gas plus HCl aqueous. This is going to be a chance to cancel out the HCl here. So I'm going to want to multiply this first, or the second reaction by 6. So we get 6 HCl gas, making 6 HCl aqueous. That's going to cancel out a 6 HCl aqueous here. But now we have 6 HCl gas that we also need to cancel out. And then also I multiplied the enthalpy value by 6. So we're going to go down the list. I have HCl gas here on the reactant side, and in 3 I have HCl gas on the product side. So that's going to be a chance to cancel out that 6 HCl gas. So I can multiply number 3 by 3 so that the 2 HCl becomes 6 HCl, so we can cancel that out. And that also gives us 3 H2 and 3 Cl2. And our value also gets multiplied by 3. And then lastly, I have AlCl3 aqueous in this first step, but I want AlCl3 solid. And in this last one, the AlCl3 solid is on the reactant side, and the AlCl3 aqueous is on the product side. So I'm going to want to flip this whole thing in order to cancel out the AlCl3, and then also get the AlCl3 solid on the product side. And then while I'm at it, I'm just doing multiple manipulations at once. This one also needs to be multiplied by 2 to get the 2 in front of the AlCl3 solid. So I flip it and multiply it by 2. So I change the sign and I multiply the value by 2. And then lastly, I have all of these equations, which should hopefully add up to the total. And let's have a look there. So the 6 HCl that we don't want here cancels out with 6 HCl here. That gives us this HCl gas that we also don't want, which cancels out with that. This H2, which is in this first equation, that isn't in our target equation, that cancels out with the 3H2 here. And then, let's see, we have 2 Al solid plus 3 Cl2. That's what we wanted for our reactants. And then the AlCl3 aqueous is going to cancel out with the AlCl3 aqueous here. And we're left with the 2 AlCl3 solid. So yeah, it looks like we summed it up correctly. And then all I need to do now is sum up all of the enthalpies to get our final value. So that is all for today, and I'll see you in Unit 7.